Hi, I'm Adam Han from the University of Nevada, Reno, and I'm going to talk about a practice for using intelligent construction equipment, and I'll use the acronym ICE, in a quality assurance program. This was developed in cooperation with the Federal Highway Administration through a cooperative agreement. Harold Von Quintus really took the lead and I assisted on it. And again, today I'm going to make the presentation. Because this is developed under the cooperative agreement with the Federal Highway Administration, there are some disclaimers that need to be shared, and I'm going to let you read them. I'll just pause for a minute. There will be 2 slides of disclaimers. Okay, so the outline of the presentation is I'm going to talk a little bit about the cooperative agreement itself and some products, then the Intelligent Construction Equipment Report, as well as some other products that have been developed associated with non-destructive testing technologies that are used in quality assurance programs that FHWA has been working on, and then wrap things up. So the cooperative agreement is titled Development and Deployment of Innovative Asphalt Pavement Technologies. The team is the University of Nevada, Reno, Paragon Technical Services, and Applied Research Associates, ARA. And really, you can look at the objective there. The point is it's really all about deployment of innovative technologies. You can find the products of this effort at the FHWA website. The URL is listed there. You can also find them at the UNR website, and you can find the webinars associated with the products or some of the products at the UNR website as well. Examples of products that have been developed are things like technical briefs and white papers, and a couple here illustrated here. On the top, you've got a technical brief on density, and actually there were a series of 3 tech briefs developed on mat and joint density, and then there's just to sort of show the breadth of the agreement. A white paper on alternative contracting methods for pavement preservation projects was developed. Again, you'll find the URLs to these products on the slides. A lot of work has been done on balanced mix designs. A lot of collaborative effort with others also on these. And there's a tech brief on 8 tasks for implementation of a balanced mix design. There's again several reports on technical reports on individual site visits and peer exchanges. And then as a final example, there's a tech brief that was developed on adjustment of asphalt mix formulas to satisfy mechanical test properties. And it's really about, in a BMD system, what are some things you can do to change the mechanical property values that you're measuring, so asphalt content gradation, etc. Okay, so I'm going to focus now on the Intelligent Construction Equipment Report, and again I'll use ICE as an acronym, and then wrap up with a little bit of other examples and conclusions. So the report that Harold and I developed is shown here, and it's called, the title is A Practice for Including ICE Equipment in Quality Assurance Programs. Again, it can be found at the FHWA website. There's a report number, and then at the UNR website as well. To start, we really have to talk about quality assurance programs, and there are 6 core elements to a quality assurance program. They include quality control, acceptance, laboratory qualifications, testing and sampling personnel qualifications, independent assurance, and dispute resolution. We're really going to kind of focus on quality control and acceptance, but we can't ignore the others because they're all requirements in a quality assurance system. And so the first thing we want to do is make sure we get quality control and process control clearly defined. And if you look at the TRB, there's a TRB circular on the definitions, and these are consistent with that, and as well as the Code of Federal Regulations. And quality control is activities that the contractor does, right? And they're required by the agency in the quality assurance specification or plan. It's really important to note that these are required and have to be reported. Now, contractors will also do process control. Process control activities would be testing and inspection and so forth that are not required by contract. That's the differentiator that's really important to recognize. Quality control is required; it has to be reported. Process control are things the contractor does. They do it on their own. They do it to make sure that the quality control requirements and the acceptance requirements are fulfilled. Some of the challenges, quality assurance challenges when using intelligent construction equipment for acceptance and payment come with validation, and it's really about using the contractor's test results for acceptance. If you think about it, this equipment is maybe mounted on a piece of equipment that a contractor is using. So there the contractor is generating the data, and if you recall, the Code of Federal Regulations requires that if you're going to, an agency is going to use the contractor's data for its basis for acceptance payment, then it has to be validated. And what that requires is that the agency, so the DOT, for example, would go out and do some testing that could be used to verify that the contractor's data was valid. And that's the validation process, and it's for example, if you looked at mat density, a contractor might have to take, 10 nuclear density measurements per lot, or 10 cores, and the DOT may take, say, 3 density measurements, whether it be by nuclear method or cores, and then those data F&T tests are done to make sure that they come from they have similar means and similar variability. Then we can say they come from the same population. Then the agency can use the contractor data in making its decisions in payment. The challenge with this equipment is if there's a compactor there, and if we use intelligent compaction as an example, the contractor's got their vibratory compactor, they're running it down the road, they're taking their measurements. The agency is not going to take and run another compactor down the road behind that compactor to get data to do the validation, and that's where this gets really interesting. So the validation can be a challenge, as well as the independent assurance. We just don't have the programs in place that are long been established for things like regular testing in the laboratories that have been done historically. We don't have precision bias statements for the actual test methods. Thankfully, we have some new test methods, and precision bias work is ongoing, but we don't have them for each of these ICE technologies. And then, of course, certification for laboratories equipment and testing personnel. With any new technology, there are basically 5 steps to basically complete deployment, and you start with the development of a concept. That's step 1. The next step is to develop prototypes, prototype equipment, then conduct field demonstration. In this example would be field demonstrations, but it could be field or lab. And then once those demonstrations have been done, you can make some tweaks to your tools that you're using, and then you go ahead and get to the pilot or first application of the technology on projects. You repeat that process again, work out some of the things that need to be worked out, and ultimately you get to the point where you can develop a specification and standards for full deployment. With the ICE technology that we're going to talk about today, we're really between stages 3 and 5, depending on the technology. And we're going to talk about paver-mounted thermal profilers, thermal imaging folks will call it. dielectric profiling systems, or DPS, and intelligent compaction. And there are some following each of these, there are some suggested uses for them. And we'll talk about, again, QC and acceptance and some of the challenges or some of the things that are not challenges associated with using them for those applications in the webinar. If we start with intelligent compaction, there's a recently published AASHTO standard. It's R111. And with intelligent compaction, we basically get an estimate of the stiffness or the response of the forces induced by a vibratory roller into the mat. And there have been efforts to correlate that to density. So what would happen is as you make multiple passes with your roller, the pavement structure becomes stiffer, right? And so the idea is as that stiffness increase, you could correlate that stiffness with density. It's been very, very difficult to do that. There are multiple things that affect density. So basically there's an accelerometer on the vibratory compactor. With that and a GPS mounted on the compactor, you have spatial information. So where is the roller? Where's it been on the mat? Okay, and again, you get the response from the load that's induced, and you can calculate a stiffness. So as I said, there have been some challenges in correlating that with density. And so this just shows the GPS and on the rollers, the operators have a screen, and on that screen, they can see it's color-coded. It's kind of like a heat map. It's color-coded, and it shows the number of passes that they've made on the mat, so they can assure that they're getting uniform coverage. So that's a very important aspect of intelligent compaction that's very useful. Challenges with using it, obviously, again, the agency's not going to go out and run a compactor after the contractor's done it. So you don't have the validation step, and so it really can't be used for payment. Again, there's some things associated with independent assurance that the loop hasn't been closed on, as well as precision and bias. We don't have precision and bias statements with most test methods, right? You have a precision and bias statement. And we don't have those for these test methods, although there's some ongoing work on that front for some of them. And of course, the training and certification or fulfilling the qualified technician requirement is not fulfilled at this point. Part of the challenge with intelligent compaction is the stiffness of the mat changes as a function of temperature for hot mix. And in that process, the density may not be changing, and that's why there's been such a challenge with correlating the stiffness response from the compactor with density. Another reason is that response is the response of the entire structure, not just the hot mix layer that's been put on the top. So that is really the drivers as to why we're unable to correlate density well. So this is still a technology that's still considered to be sort of at stage 3. It's a great tool for monitoring number of passes and mapping to make sure that good coverage has been completed. It's also a tool to identify prior to placing your surface lift or the next lift of your hot mix, prior to identifying weak spots, utilities, all those kinds of things. So variability in the existing mat before you even pave on it. The next technology I'm going to talk about is a paver-mounted thermal profiler. And again, there's an AASHTO standard for this, and it's an AASHTO R110. And basically what we get with the thermal profiler is an estimate of the surface temperature of the mat. And so an IR sensor is mounted on a paver, and it gets, as this slide illustrates, it basically allows you to get a transverse temperature profile. And then as the paver moves longitudinally down the mat, you then have a complete longitudinal and transverse profile of surface temperature of the mat. And some work done by the University of Washington, or it was really by the Washington State DOT, and UW helped them with it. They found that if you have excess ranges or variability in your mat temperature, you're going to have variability in your mat density. And that work was done, I think, in the late 90s, if my memory serves me right. So it's not something new, but this is some technology that can help identify the potential for that. So again, it's very simple hardware. On a paver, you basically have a GPS mounted on the paver, and then you have an IR scanner. And there are different ways of mounting them. And today, pavers can be, you buy a new paver today, it's not uncommon that they're installed by the factory. They're not sort of aftermarket bolt-ons. The systems all have their different manufacturers, and they all have just like the monitor on the roller, so the operator can see the pass coverage. There is a monitor, and it shows the temperature, so the thermal profile, as the paver goes down the road. And it's a heat map, and it's color coded, and that's what you see over here on the right. And in this example, the color goes from the low temperature blue, and the highest temperatures are up in the purple range, if you will. And what's really important, one is what the temperature is, but also the uniformity of the temperature. So the more consistent the color is on the map, the more consistent the map temperature is. This is just an example of some of the hardware. Again, it's not much to it, and it's a simple bolt-on, if you will. So what do we get from the thermal profiler? Well, we get surface temperatures, and we get a map of it. And this is a heat map in the top right. And you see there's an array of colors here. This is on startup, right? So you have temperatures that are the lowest down here, probably around 275, 280. And then you have temperatures up to about 310 degrees. Okay? We also get a diagram of the paver speed. So this tells you about the operation of the paver, and of course you can identify stops with this also. We've all been trained that we want to get our paving operations up and running and run at a constant pace, so that we have a balanced operation and we're feeding enough material to the paver so the pavers never run and dry, and we're going slow enough so that we've got adequate, with the compaction equipment we have, we've got adequate opportunity to get it compacted before it cools. And again, this can help operators understand the influence of speed changes on their operations, and ultimately density. There's basically like a histogram, and you get what they call it a class diagram screen. You get a distribution of the percentage of, or the count, which is really can convert that into a percentage, of temperature observations that are in certain ranges. And in this example, you see that we've got a handful down at 250. There are about a little over 20% at 270, about 75% at 290, and then there are a few at 310 degrees. So, and then finally, again, we get the map that shows where stops occurred. So the challenges with implementing this technology is the validation. Again, the IR sensor is mounted on a contractor's paver. So for the agency to go ahead and get a heat map, they'd have to do the same thing, right? And so how do they independently do that? That's the real challenge. If they don't get that data, then you can't use it for the verification and validation processes. And so there's really no consensus right now on how to get that data or validate it. We also have some needs associated with independent assurance requirements, and therefore it's not suggested for use for contractor payment at the present. The tool was really brought to light through a Sharp 2 project that actually Harold was very much involved in. And there's some data that we're going to share here that illustrates some of the benefits of this, and they're associated with identifying differentials in temperature, longitudinal streaks. Depending on your paver setup, you can sometimes have streaks in your mat that are at different temperatures. The benefits of using material transfer vehicles, the benefits of tarping, the influence of how you load your trucks, and all that stuff can be used by contractors and agencies to improve the consistency and quality of the mat. This is a profile data from a project, and just what I want to show here is the heat map. So this is the start of a lot, and you see multiple colors here. This is near the center of the lot. Okay, we're getting more and more yellow, less orange, less green. Again, those are the extremes. And near the end of the lot, it's almost all yellow with a little bit of orange. So this is a transition, if you will, from relatively high variability in mat temperature to reduced variability in mat temperature, which again will lead to more consistent density, which is obviously very important. This is an example of a contractor using field data, getting it back to the lab in a timely fashion, essentially real time, so that they know what's going on at the plant, and the quality control folks can help the plant operations and field folks be successful by using the data. So I just mentioned a couple of examples there on the demonstration project associated with the Sharp 2 project. One had to do with trucking, and I talked a little bit about balancing operations. We got consistent operations, and on one of the projects, demonstration projects, they added some trucks, and by adding trucks, they reduced the what are called temperature differentials, and I'll talk about those and sort of quantifying in a minute, significantly by adding trucks. So the range of temperatures on the mat went from about 30 degrees Fahrenheit down to about 15 degrees Fahrenheit. Another example was associated with loading trucks. So loading in one drop versus multiple drops, and with the multiple drop technique, having more consistent temperatures of your mix on the mat. Now this table is very informative. We have to take a minute and look at it because there's a lot going on here. So what this is it's got on the first column, you've got locations that projects took place. Again, this is Sharp 2 work. You've got the delivery truck type. So the first row has a bottom dump. Okay. Then you see end dumps with the rest of it. And then the third column shows whether or not an MTV was used. And then the fourth column has percent severe temperature differentials. And the definition of a severe temperature differential is greater than 50 degrees. So those are pretty significant temperature differentials. And what's reported there in that fourth column is the percentage of them. So if everything except for the first row is bottom dump, so let's look at all the end dump stuff, okay? So starting with Missouri down through West Virginia, we've got end dumps with MTVs, and we see that the percentage of severe temperature differentials ranges from 5 to 25%. And then when we go to the last three rows, again with end ups without an MTV, the percentage goes up significantly from 40 to 83% of the temperature differentials were severe. That obviously shows that going from end dumping to right into the paver to an MTV can significantly reduce the amount of severe temperature differentials. Nobody's selling any equipment here or anything. This is observations. And now if we go back to the first row and we look at Alaska, so this is a project there where there were bottom dumps and a windrow. When you have a windrow, you have to use a windrow elevator or pickup machine or a coal cow, pick your terminology, to get the mix into the paver. And on that project, and there's only one of them, so it's a little hard to sort of make any real strong comparison here, but it does illustrate that even with bottom dumps and windrows, not an MTV, you can still pave and have mats with a relatively low percentage of severe temperature differentials, which is illustrated. So really what that says to me is that if you're doing the right things, right, in your paving operations and you're using the right tools, you don't necessarily have to have an MTV to get consistent mat temperatures. So with the thermal mounted or the paver mounted thermal profiler, it's not used for acceptance. It's again a great tool for monitoring paving operations and making corrective action. There's so many examples of that, and I'll wrap up with some of that in the end. So some of the challenges are obviously with the laboratory and personnel qualifications, and you think about it on these lab qualifications. If you pick a lab test, I don't know, theoretical maximum specific gravity, you've got a pycnometer and a shaker table, and you got a manometer, and you have balances that you use, and you have a calibration service come in, and they verify the performance of the equipment and give you records and all that good stuff. Well, that's not going on out in the field, right? With this equipment. This equipment is mounted on a paver, and so we just don't have some of the systems in place to make sure we meet the independent assurance in laboratory, what would traditionally have been called laboratory and personnel qualification requirements. Because you have to make sure that the sensors are working properly, and you have to go through a process of calibrating them and then verifying them at a given frequency. And again, that's just not really worked out just yet. What is included, or what was an outcome of the SHARP 2 project was a recommendation, though, on defining lots, okay, as the distance that a single truck covers. So the reason for this is when you're looking at this data from truck to truck, right? You're not looking within a truck. You're obviously going to see more. You have the potential to see more variability, right? But you're not really looking at the control within a truck is which really matters. Assuming that the plant produces a mix at the same temperature and all that good stuff and gets loaded the same. So that was one of the recommendations, and these are the tolerances and the definitions of low, medium, and high tolerances for temperature differentials. And I said a minute ago that severe was the high, and that's over 50 degrees Fahrenheit. Medium is between 25 and 50 degrees temperature differential across the mat, and low is less than 25 degrees. And I already talked about the independent assurance items, and then finally the dispute resolution. Again, this is a tool that can be used to help dispute resolution. So the questions posed, is there benefit? Obviously, yes. Will it result in reduced maintenance costs, more consistent mats, all that good stuff? The answers are yes, yes, yes. And then so a follow-up question is, why aren't more contractors using them? And as there are some contractors, I should first start by saying that there are some contractors that are using them and using them successfully. The other piece of that is contractors have businesses, and so if they're going to make an investment in this technology, they've got to buy the equipment. They've got to have people that are monitoring the data constantly, putting all that data up in the cloud, storing it, and analyzing it, and then using it for training. That all costs money. So if there's not an incentive to do that, some contractors may not do it. The next technology I'm going to talk about is a dielectric profiling system, or DPS. Some of you may have heard it referred to as GPR, ground penetrating radar. And basically what the DPS is, and there's an example of the picture on the right. What's typically being done today is that you've got a cart, you've got 3 sensors mounted on it, the orange what look like boxes on the cart. The cart is walked down the mat. Each of those sensors, you obtain basically from each sensor a dielectric constant, which is, and then we don't have time to get into the details of it, but essentially you get a dielectric constant from each of those sensors, and then you can correlate that dielectric constant with density. You can correlate it with bulk specific gravity. You can correlate it with percent compaction. You can correlate it with percent air voids. It doesn't matter, whatever one you want to. But the point is, you get a dielectric constant, and then you correlate that with density. One of the really good things about this is you can get full mat coverage. So rather than taking 10 density measurements with a nuclear gauge, or the state taking 3 cores or 10 cores and 3 cores for the contractor in the state, or 10 nukes and 3 nukes, you can get complete coverage. So you can get a measure of conformance rather than an estimate. When we take a limited number of samples, most specifications, we take a limited number of samples, say again, contract taking 10, agency taking 3. The F&T tests are then used to verify that the means and variability of the data are similar. If they are, then the contractor data, which is a bigger data set, is then typically used to calculate a percent within limits, which is an estimate, right, of the percent within limits based on a sample. And it has, you know, some risk associated with it. And really, all that is eliminated if you get a complete mat coverage, right? So you'll, at that point, you know everything about the mat, and all you have to do is look for how much doesn't conform. And there's no estimating from a sample, which again has some risk associated with it. You can also use it to measure density transversely. And again, this is a really good tool for pavers, for paving operations, to understand the influence of how they've got their paver set up and how they're operating it can influence density, as well as the compaction process. So this slide shows correlations between dielectric constant. On the x-axis you have asphalt layer dielectric value. On the y-axis you've got bulk specific gravity, and again with a theoretical maximum specific gravity you could turn that into density or air voids. And you see the correlations on these plots in the 0.7 to 0.75 range, and these are basically from correlating dielectric values from the GPS or DPS to field cores. Now there is a lot of variability that can occur, right, in production. So you have, and we talked about temperature gradients, for example. You have inconsistency in mix. You have the distribution of the mix with the paver and how that could influence all of this. And so at the end of the day, there's a fair amount of variability in the field that doesn't exist in the lab, and that became an important future observation for future use. So the things that influence the dielectric in the field are the whether or not the mat has any moisture on it. It has to be dry. The dielectric is significantly influenced by moisture, and so the mat has to be dry. So it's not sort of real-time density. It's when the mat's dry, but in most operations it's pretty quick, after the mat is dry. I mean, after the mat has been finished compacted. And then the thickness of the mat, as well as the gradient of the density in the mat itself. Okay, so the variability associated with that has created some challenges with getting those really good correlations. So getting above about a 0.75. Now there's some rare cases where it's better than that. So what has been learned, and there's been a lot of work done on associated with the pool fund study that Minnesota is the lead on. There's a DPS ETG, and again, I think there are 20, I don't remember the number of states, well over 20 states, close to 30 states that are participating. And one of the outcomes of that is using laboratory compacted specimens to develop the correlation between density or air voids and dielectric value rather than field cores, to address the fact that there's so much more variability in the field and you're really trying to get an indication of the density. So we see here an example of a correlation that's 0.99, fantastic correlation, right? So this is what is being used today or promoted today. This is an example of some data with both cores that were measured, so it's a volumetric air voids, cores that were calculated, so bulk density and RICE were used, and then lab compacted specimens. And you see pretty good correlations among them, and again, R-square value that are very, very high. But most folks have begun to move to using lab specimens to eliminate those other sources of variability and get better correlations. So there's a provisional standard for the DPS. Obviously, there's some Challenges when using it associated with acceptance and payment. Again, this is one of those where if the contractor goes out there and runs the DPS over the mat, gets all the data, the agency has to use some method to verify that, whether it's CORS or running a DPS on a portion of what the contractor ran it on. And so you know, it's not recommended right now for use for validation because of that process. We still have some things again on the independent assurance to get worked out. There's work going on the precision and bias, which is really good. And then again, training and certification for quality assurance personnel is still something that's sort of hanging out there. Again, a lot of this is being worked on that pool fund study. I don't want to, you know, underscore, or I do want to underscore all the really good work that's been done on that, and FHWA has been supportive of it. So the tool is a really good tool. The DPS is a good tool for estimating mat density, and again, you get the complete coverage. We can correlate it with density. We can use it longitudinally or transversely. The one thing that states could do, or agencies could do, is they could do these measurements themselves rather than having the contractor do it, and then use it for acceptance. Okay. Again, I think it's a great QC tool and a great training tool. I've been on projects, you know, where contractors have used these technologies, all three of them, intelligent compaction, thermal profiling, and DPS collectively to understand problems. And again, they're great tools for changing processes and for training, in my opinion. And I've already sort of beat this to death. You know, with a lot of these technologies, we have the laboratory and personnel qualification requirements that we need to get, again, worked out. And again, it's different than what we've had in our historical quality assurance programs, where we're really focused on labs. We got it out in the field. You know, we can establish relationships between density and dielectric value, and it's again a very good tool, and it has been used to help with some dispute resolution stuff also to date. So is there a benefit? Obviously, the answer is yes. Will its use result in more accurate decisions? Well, because we have the potential to measure the whole mat rather than just spot sample test. Obviously, the answer to that is yes. So again, the question is, how do we get contractors to use it? And I think the answer is really the same, right? They have to find a benefit in it, whether it's you know, improving their pay factors on PWL projects, or you know, getting materials accepted that they've historically had challenges with. And again, the pool fund study, a lot of work has been done that I think is going to help us continue to get to the point where more and more contractors use it. In wrapping up, I'm going to cover a couple of other things that have been going on with FHWA associated with using non-destructive technologies in quality assurance programs. One is the quality and asphalt paving process. So the Mobile Asphalt Technology Center, which is, some of you may have remembered what the mobile asphalt labs, or whatever they were, used to be called, the binder and mix portable labs. They will do these quality and asphalt paving process workshops, and they cover quality assurance concepts and then positive practices for handling, testing, inspecting, and paving processes, and they'll include the DPS, thermal profile, and other field devices. There's one for thickness in there also, though. And there's you can find the document. Oh, I thought I had the URL on this page. I apologize. To this document, which is a write-up about the quality and asphalt paving processes. You can find that at the FHWA website. They're also doing spotlights on pavement uniformity. They've done one on the thermal profiler and one on the DPS, and then they've got also the spotlight on pavement uniformity documents that are examples of where different states have gone out and used them, and what their experiences was. And again, you can find those on the FHWA website. So this is the stuff associated with thermal profiler. These are examples associated with the density profiling system. So again, it's good examples of using the tools to improve quality. And obviously, if we improve consistency and quality, we're going to get better performance. In the long run, it's going to save agencies and taxpayers dollars. The last thing I'll talk about here is NCHRP Project 10108. And from that, a manual for incorporating non-destructive testing and quality assurance programs was developed. Obviously, the some draft standards came out of that. Some of those draft standards were have transitioned to current standards, which the one for the intelligent compaction, as well as the one for the thermal mounted, the paver mounted thermal profiler. And we talked about AASHTO 111 and 110. And so with that, as far as takeaways go, these technologies represent opportunities to positively impact asphalt pavement performance and give contractors and DOT spatial quality information. The thermal profiler evaluates the uniformity and magnitude of temperature variation in real time behind the mat. That's the surface temperature. The DPS evaluates the uniformity and magnitude of the asphalt mat density after compaction. Again, it's not real time, but it can happen certainly very quickly after completion of paving, although it takes some time to analyze the data and all that good stuff. And then intelligent compaction evaluates the change in asphalt mat stiffness during rolling as a function of time. It also shows, again, pass mapping, and I personally, I think that's a really, really good feature from a QC perspective or a process control perspective. Thermal profile is a non-destructive technology that provides good process control and QC data. The DPS is again an NDT that can provide acceptance data to the owners if they make the measurements, again. DOTs could make those measurements themselves that could be used for acceptance. And again, contractors can use it for process control and again, learning and training. IC requires quite a bit more work to get to the point where it could be used for acceptance. And combining these techniques can be really powerful. And to that point, there was a workshop at TRB last January on this topic. And then there was a webinar associated with it that was done in May of 2023, and it's called Real-Time Quality Control with DPS and PMTP. And the folks that did that included two contractors presented at the workshop. Two contractors presented examples of using the technologies and coupling 2 or 3 of them very, very successfully to improve operations and resolve problems. This is a URL to the recording of that webinar, and I would really encourage you to go take a look at that. It's it talks about some of the things we've talked about today, as well as again demonstrate some examples that are presented by contractors using the technologies. With that, on behalf of Harold and myself, I'd like to thank you for taking the time to watch the webinar, and thank FA Segway for the opportunity to do the work, and encourage you to go, again, watch this video and look at the documents and use them to leverage your improvement in paving operations. Thank you.